Okay, testing, 1, 2, 3. Hi, and welcome back to the Raspberry Pi do-over. Hi, and welcome back to the Low-Level Devil Channel's Raspberry Pi Bare Metal series. In the previous video, we covered the turning on the MMU so that we're able to actually write using unaligned data, which will be required if we want to start doing some disk access. So in this video, we're actually going to start doing some disk access, and we're going to implement the Emmc. So let's get started. Now, first of all, I want to go over a little bit of house cleaning here. Also, first I want to mention in this video it's going to be a little bit of a different format. Since there's so much code to go over, I'm just going to kind of walk through the code instead of doing the live coding and typing it. It'll just make things a lot easier since we got a lot to cover. Also, I did some rearrangement of the code here. You'll see these different folders. I have a folder for boot, one for DMA, then a section for drivers. So I put Emmc under there, the GPIO, all the different things which I'd consider drivers I put under there. Let me think, some other small changes. The video, for instance, let's see, in this section here, before we were kind of hard coding where the video buffer was and the BG32 buffers. Now we're using that new allocate memory function to grab those. And also, I believe the same for DMA. There's another situation where we were hard coding memory locations. We're just using the allocate memory there now. And I think there was one more thing that I wanted to cover. No, I think that's about it. Oh yeah, in the make file, the changes I had to do to support this, I just changed the C files section and the ASM files section, so it'll load star and /star to find other files. So that supports having a couple of levels of directories here. Okay, so let's move on to the Emmc. I don't think that the Raspberry Pi 4 documentation really covers it, but the BCM2835 really does pretty well. It's still kind of sparsely documented, but at least it documents all the registers involved. So if you look at section 5, which I think is page 65 here, that's where it starts talking about the Emmc, the external mass media controller. So it talks about all that here, and like the first section here is the address map where we have the different registers that are involved in it. And like I do with other drivers, I'm essentially kind of mapping this to a data structure that we can write to these registers. So I won't go too into detail on these registers because all the data's here, and I've kind of shown you before how to walk through these and understand what the registers documentation is like. So I won't get too deep into that just because there's a ton of code to cover. Another thing, I was trying to find a good resource on what the actual SD and SDIO communication is like for the cards. This website here, I'll put a link in the description. It goes pretty well over it. It goes a little more in depth than we even need to go because we're not doing direct SPI communications or something. We're using hardware communication for it. But there is some useful stuff in here. It talks about the command format. Each command is essentially a 32-bit data packet that you send, and it can have a response with optional types of responses. Sometimes it's one 4-byte packet coming back. Sometimes it's 4. Depends on the actual command. There is some decent documentation on some of the commands and like the different flows. One of the important flows here, if we scroll down here, there's a good flow. Yeah, this would be like the initialization process. So when you're powering on, first you need to send command 0 here, then a command 8, command 5 with argument 0 to get the OCR, then followed by command 5 with different argument that we pass to, and let's see, goes down here to sending this A command, which is an app command 41 to get a memory OCR, and then we send it again with some more details to get the high capacity support host flag. So this is all the process that's kind of needed before you can actually start really using the card. So it's kind of the initialization process. So you'll see we have a reset function that kind of mirrors what this flow is here. So just so you can understand from the code where the whole idea of it comes from, like why we're doing all the things we're doing, you'll be able to see some of that in here. This does cover the actual command format some, but I think it's not completely complete, and it does document some of these commands here, but not all of them. We're only going to be using a few of them. I only want to have enough to be able to read and write to the card. Not doing anything fancy like DMA yet. I just kind of want to get something started. So something started that we can use and actually start reading from the disk from. So let's jump right into it. So we'll start with, under include peripherals, there's the Emmc header, and put some debug define in here that we can use. And there's this little macro to swap bytes, which is essentially reversing a number from big endian to little endian. So the Emmc command is actually, this is one 32-bit number that I've separated out into little pieces. Like this first bit is the resp A, the next bit is whether it has a block count, this bit here is for direction, whether it's a read or a write. This bit holds the response type, and the response type can be one of these values, whether it's going to have no response or the different sizes of the response. So some of this data you'll find in that URL that I mentioned. I have a little defined here for a reserved command, which is essentially all the bits set to 1. It's just a way to say, this command is either reserved or I haven't implemented it. Then I have command types. I put together an enum, so like the go idle command is command 0, the set CID is command 2, the OCR check is this command 41, for instance. And actually jumping over into the code for it real quick, just to show you where that's coming from. So in an Emmc we have the actual array of all the commands, and I kind of initialize each of the commands here. So it's command 0, this is command 2, 3, 4. These are the different properties that each of these commands have. Most of them are reserved, so there's only a few that we're actually using. So I kind of put them here in an array so we can easily look them up. And this maps directly to that indexed value in here. Let's see, then there's just a data structure for the SCR register, some error codes, an Emmc device. This is actually some of the status stuff that we have for our device, whether the last command was successful, what the last command was, its value as a 32-bit number instead of just the CMD structure, the block size, the last response, the buffer, like if it's got a read or write data, the buffer that it's using. So these are all just the kind of state of the Emmc device. And then our register structure, so our Emmc reg, this maps directly to this here. Okay, and you've seen how I kind of do these before, so I won't go too in depth over it. Then a little utility function to convert to a register, actually just to a U32. This command structure, it's going to convert it to a number, because in some cases we need that number. Then some defines. Some of these I'm using and some of them I'm not. These are different, like clock frequencies. a little bit of this code is taken from the Raspberry Pi Circle project. If you're not familiar with that, let's see, github.com RSTA2 Circle. So this is an open source Raspberry Pi bare metal project. It's in C++. It's not very well documented, but there's a ton of code in here. So if you want a really complete implementation, this one's probably more complete. On this one, I'm kind of doing it for a video, so I want to do the smallest amount I have to do to get things working. So let's see. Then I have some defines for init, read, and seek. I'm not implementing a write function. I do have the guts for the write, but I'm not implementing a write external function yet until I have a file system that I feel I can safely write to. Otherwise, I'm going to end up destroying the disk. And some defines, like for the Emmc control 1 register. Let's look again in here. So the control 1 register, skipping down. There's control 0 and control 1, and status register. So control 0, there's a couple of bits that I have that I need to actually use. I just put some defines for those, for control 0, 1 and control 0, and then some for the status bits. So these will map directly into the registers and what those bit values are used for. I kind of separated the eMMC into two files. One for setting up the clock, because it's kind of a lot of complex code there. I just wanted to separate it out so the file wasn't too big. Most of this code I actually took from the Circle project, because I didn't really understand all the different clock divisions that were necessary in this, so I just kind of translated their code into this so I could just get the thing working, essentially. But there's a get clock divider, switching the clock rate, and because we need to actually enable the clock using this control register. First of all, actually, let's see, we need to loop while these command inhibit and data inhibit flags are set, and then we can enable the clock. And then there's a whole steps that you have to go through. You have to set unset the enable, wait for 3 milliseconds or so, and then you do some other stuff, setting the divider, wait for 3 milliseconds, and then enabling it, and then wait for 3 milliseconds, and then you can actually use it. So yeah, I have this eMMC setup clock function that I'm using inside the main eMMC. This actually uses that mailbox API too, which is a reason I wanted to get that done before I could get to here. So let's see. Yeah, I think this is enough for the clock. I'll jump over to the eMMC code. So yeah, I exported these two functions here, or I guess you say to import them. Then we have our main device object, and then our eMMC command. This is just a representation of an invalid command so that we can compare and make sure a valid command was sent. Next, moving on to this wait register mask. So this is a kind of a utility function. We'll pass in the address of register, and this is essentially going to loop until the mask that you pass in is either set or unset, because sometimes you want to wait for a flag to get set, sometimes you want to wait for a flag to be unset, and then a timeout. So it loops through, it sleeps for 1 millisecond, so our timeout is in milliseconds, and it'll return false if it times out. And we went over this commands thing here. This is just a utility function to get the SD error mask, and something to set the last error. So do data transfer. I'll get back to, I want to start with the process of, let's see, let me scroll down. Like the first thing that we need to get into is actually issuing a command. So there's a function eMMC command. Let's see, the first thing it's doing is checking this 1 bit, because this would mean it's an apt command, and we have a different function for using that, so this will return false in that case. Then it checks to see if it's an invalid command. If so, it'll return false. Then it runs the internal Emmc issue command, and the Emmc issue command is what's actually going to be sending the command using the registers, reading and writing data if needed. So let's see, first of all, we're just grabbing the actual register value, storing it in our last value command. We check the transfer blocks. If they're not too big, if it's too big, then we have to return false. We're setting the block size count, setting the argument into the argument register, because some of these commands will take an argument, so we set the argument register accordingly. And then there's a command transfer mode, which we set to the actual command itself, the 32-bit value of that command. So after we set those, we have to sleep 10 milliseconds, and now we're going to loop through a kind of check on this interrupt flags register. So once the interrupt flag register is set to this value, then we know it's done. And if it's gone too many times, we'll say it's timed out. And actually, in some cases, I'm setting this as a warning in the printf statement, because in some cases, some of these commands, it's okay to time out. But yeah, we'll get into that later. So let's see. Then we get the interrupt flags. This is how we kind of determine if it was an actual error that was returned. So if the interrupt flags have this a certain value not set, then we know, oh, okay, that was an actual error in the command. And then we'll set the last status to false and set the last error data. And then we're just printing out some debug information about it. So then based on the response type of the command, we have different ways that we handle it. For instance, these two ones are actually going to be a 132-bit value response. So we read that from a response 0 register, and then that's our response. These ones will actually have 4-byte responses. So in those ones, we just set that value from the response register array. So then we do, if it's a data command, we do our data transfer. I'll jump back to that in a second. And let's see, if the response type is busy or if it's an isData command, we have to we do a wait on this one register flag, and it's okay if it times out here. So then we grab the interrupt flags again. There's some special checking that we need to do to actually see if it was an error. So these top flags are the ones that we kind of are just masking off, and the bottom two is what tells us whether there's an actual error. So then we have to set that back to this value after we're done that check, and then we can say, okay, it was successful, and we can set the success to true. So the main problem is, like, these response types, the data response and busy response, we need to make sure it's finished actually processing. So that's why we have this this whole section here, and the timeout of essentially 2 seconds. So it shouldn't take more than 2 seconds to complete any of these commands. So let me just jump into the do data transfer function. So when we do the data transfer, the first thing we have to check is what's the direction of this command. You know, is it a read command? If so, that we have to set this bit. So 1 shifted over by 5 on this register here. Or it's not a register, it's actually a value we're going to look for on the int register. So and then 4 for a write. So then what we do is we take the device buffer, grab it here as a 32-bit value, and now we're going to loop through each blocks from 0 to the number of transfer blocks. So for each of the blocks, we need to actually do this wait command based on the type that was passed in. on the interrupt flags. So everything we're doing through this interrupt register rather than actual CPU interrupts. So that's something that you can set during initialization. I should probably jump to initialization over here, but I wanted to at least cover the command so you have an idea what a command's doing. So let's see, we're doing some checks on the interrupt register after that return, and checking to see if it's an error. If so, we set our last error and return false. Otherwise, what we do is we'll get the block size. So we need to loop through the length. And if you remember, these are 32-bit values. So we're doing a minus equals 4 for each of these. So we're looping through length times divided by 4 and sending a whole 32-bit value at a time. So we're either, if it's a write, we're setting eMMC data to the value of this data and then incrementing it. If it's a read, we're reading this value and incrementing it of the eMMC data register. Hope that makes sense. I'm kind of going through this fast just because there's a lot to cover in here, and but again, we have a Discord channel, and I can answer questions of if you have more detail that you want to know. If you join the Discord channel, which will be in the description. So now that we kind of covered what a command is and the process of actually sending a command, let me go to the initialization part. So right at the very init section, IO device register. This is something else I wanted to cover. So I'll get back to this later, just because I wanted to kind of cover it more in depth. I kind of wanted to do that at the beginning, but I'll just do it afterwards. So the first thing we're doing is most likely not necessary, but these are the pins that are used, and if for some reason they get reset to some other alternate function, we need to reset them back to what they should be. So I'm doing that in the init just in case whatever bootloader we end up using, ends up changing these functions. So that I'm initializing the device, some of these things like transfer block to 0 and last success to false, just doing some basic initialization. Then what I'll do is loop through 10 times trying to call eMMC card reset. And I'm looping 10 times because sometimes it actually fails on the first read. I find it fails more often on the Raspberry Pi 4 than it does on the 5, and it also depends on the card that I'm using. Some cards, maybe they're just not as good quality and it takes a little more massaging to get it to work right. So we're retrying some of these commands until they succeed. So jumping into the eMMC card reset, this is the actual initialization process. So the very first thing we have to do is on the control 1 register, we have to set the reset host. And again, that's in the data sheet. You'll see that in here. This was it, control 1 register, yeah. So these, am I looking at the right one? Yeah. So, no, that's not right. Let me look at this. Yeah, so, but, yeah, okay, bit 24. So bit 24 is a reset host. And then reset all, this one is, we want to reset the entire host. And then the reset all command is all 3 of these resets set. So data, command, and host. So what we do is we set the reset host, and then we're going to wait while any of these reset bits are set. So after 2 seconds, if they're not set, then we're going to say it timed out trying to reset the card. So that's the basic reset, but then the rest of this is all initialization. There's some special code here that's done only on Raspberry Pi 4, and I don't really see any documentation of this bits on the control 0 register. So I'm not 100% sure but I've seen it in other projects and it works when I use this and it doesn't work when I don't. So from what I can gather is it's used for enabling VDD1 power bus for the SD card, and you actually need it for the RPi4 or it won't work. So we'll just take that as stolen from other projects such as Circle. The next thing we do is set up the clock, which we talked about before in that Emmc clock thing, because until the actual clock's set up and synchronized on the card, none of the commands you're sending are really gonna do anything. So moving on to that, we set int enable to 0 because we're disabling interrupts for the CPU, and we're using the actual interrupts on the interrupt register instead. So that's what these here are set to do. After doing that, you have to sleep a certain amount of time, 203 milliseconds for some reason. Then I'm just doing some extra initialization here, and then I start the very first command. And this is where you see from, let's see, our SDIO, the URL that I sent you. This is going to be essentially this processed here. So the first thing we do is send the go idle command. That has to respond successfully or we're done. Next thing I'm doing is checking the V2 card. So that involves sending this command, so command 8, and we have to send this specific value. And let's see, this one I think is one. Yeah, this one can't time out. So there's special handling we do if it's if it failed, then we know this was a timeout. This one we know it actually was a specific type of error. So actually this last error is 0. So there's a couple, I guess a couple of different timeouts. There's an actual, the command timed out, it took longer than this amount of time, or if we actually got a timeout error back from the from the command, and in which case we can call this reset command, and if that's successful then we're good and then it can move on to here. So if we do get a success back from this, then we know this is a version 2 card. So I guess if it's a version 1, it might just time out, and that's okay. We just know it's not a version 2 card, so it's okay to just reset that command. So, and resetting command uses that reset flag. So this reset command, that's control 1 reset 1 command flag, and then just kind of loops until it succeeds. So let's see. This is because we support V1 and V2 cards, so V1 card would go through this route instead. So let's see if we can go back to here. So after we get whether it's a V2 card, we check to see if the card is usable. So checking to see if the card is usable involves sending command 5 with option argument 0. And this is another one that may or may not time out. So this one is actually okay to time out. So I don't have any logging in the timeout section here because it can be okay for this one to time out. So that'll still return true as long as reset is successful. Oops, well, let me go back here. So now after checking with the card is usable, we have to check for the OCR, and I think I remember what that stood for off the top of my head. OCR. Yeah, I remember seeing it somewhere, but I already forgot what it means. It's a certain value that's just required for us to have to really be able to use this card. Well, we actually get it from the response, so that's where we send this app command 41. So that gives us the OCR value for this card. In this check, we're actually looping through 5 times because sometimes this will fail the first or second time. So I just kind of loop through 5 times, and if it passes, then good, then we're good. Otherwise, it'll just send an error saying that the command failed. So then we grab the OCR from the bottom section bits of this response 0. So then we'll set the device OCR, and then we know we're good to go. Then we check for this HDHC support and passing in this V2 card value, because if it's a V2 card, we set some extra flags for our check. So in this one, we're kind of looping while the card is busy. We're again sending this app command 41, and we send this. This is the argument we send with the flags, which we're passing here. And so if that fails, then we know, then it's just no good. Otherwise, if the response has the, it will have the OCR again. So we're kind of resetting it there again, and it'll have this flag letting us know whether the SDHC support is enabled for this card. So then we're just kind of looping while the card is busy. So if it's busy, this flag here isn't set, so we'll just kind of sleep for 500 milliseconds and try it again, because in some situations the commands can still be busy processing the previous one. So let's see, moving back to here, now we actually switched the clock rate using this these eMMC functions here. So we set it to this value that we need it to be, and passing in the base clock and then the value we want it to be. After doing that, you have to sleep an amount of time, 10 milliseconds we're doing. So then we need to check the RCA of the card, and this is kind of important because this allows us to select the card based on its RCA card ID. So in order to do that, we send this command to here, send CIDE, with 0 as the parameter. Let's see, for some debugging info, I kind of put the card ID here. It's just like a unique identifier for the card. Let's see, and then we have to set the relative address after that, just calling this command, and that will give us back the RCA for the card. So this one gives us the card ID, this gives us the RCA, so relative card address, I guess you call it. So we take this value, shift over by 16, and mask off those bits to get the RCA. And then in the debug, I kind of have, there's the values that we get from that response. You know, print out the RCA, and we can see if there's a CRC error or command error. These are different types of errors that can happen, and these flags will be set in the response if that's the case. And then the ready flag. So pretty much these should all be 0, and this one should be set to 1, letting us know that the card is ready. And that's why we're checking that again here. That's the ready flag. So if it's not ready, then we failed to read the RCA and we return. Otherwise, it's true. Alright. So now we want to actually select the card. That's the next step in initialization. So to do that, we're sending command 7 with the RCA shifted over by 16. That's how we select that specific card. This will succeed if we can select the card, and then it'll return us a status, and the status has to be a couple of values. It has to be either 3 or 4. Then we know it's a valid status. And then setting the SCR, I think this is the last step in the initialization process. So first we want to, if it's an SDHC card, we have to set the block length to 512. And then let's see, so now we're grabbing the block size count, mask off these bottom bits, and then set it to 512 essentially. And then we set the register again. So, and then our buffer. So for the buffer, we're passing in the address of this SCR variable on the device, which we had pulled out which we're actually using for this command. And then our block size is set to only 8 because I think this is, you can see this is an array of U32, so it's two 4-bit things. So that's why our block size is 8 and only one transfer block. And then we do this one app command, which is app command 51, and that one it's given 30 seconds to time out. I guess this one can take a little while to set up initially. So that one will succeed and we'll get back our SCR, which we need to use that bswap method to swap from big to little endian, or the other way around. Then we're setting up our version. I'm just setting it to all bits set here initially, but we actually pull the version out of this SCR response, SCR0 response. This is kind of a lot of bit manipulation here. We need to find out which spec it's using. If it's spec 0, then we know it's a version 1. If it's spec 1, then we know it's 1.1. If it's spec 2 and it's not spec 3, then we know it's version 2. If it is spec 3, then so there's different values. That it's kind of a little complex thing. This I also took from the Circle project, because they had that laid out, and I couldn't really find any good documentation on what all this means. So I kind of just took the version data out of there, so we have it if we need to use it down the line. So after all those initialize startup command process is finished, then we set the int flags, reset all the flags for the interrupt register, and then we say the card is reset, so then we can return true. So this is how you initialize the card. See if there's any other things that are in here that I didn't cover. Yeah, I tried to separate these things out into smaller sections to make it a little easier to read and understand. Like I said, this command structure should support reading and writing, so there's different commands. Let me see in this command list up here, like reading a block, read multiple, writing a block, write multiple. So all these commands should be supported. It's just that I'm only exporting the use of reading and seeking for now, because I'm a little afraid to write to the disk and break it until I have a working file system. So this seek actually is down here, Emmc Seek. So what seek actually does is this will just kind of set the device's offset to whatever you pass in. Really simple. And then read is going to do, so Emmc read, first of all, the offset has to be in a multiple of 512. If not, then that's considered an error, because to get the block that we want to read, we have to divide it by 512. And this all works really well with like disk systems, because in file systems the blocks are usually 512 byte blocks, like sectors and all that. So then what we do is we say we're going to read this block, and then we'll return an error if the read doesn't return the size that we expected. So the do read command essentially just sends this do data command, which the very first field is write or read. So we're passing false because this is a read. Then we pass the byte data, the size, and then the block number. So the do data command, that's this one up here. So do data command has some special handling. If it's a SDHC card, we have to multiply the block number by 512. If the block size is less than the device block, if the size of the buffer is less than the device block size, then that's invalid. We're setting the transfer blocks to the size divided by the block size, and then we're making sure that size is not actually a multiple of block size, so because it has to be a multiple of 512 or whatever the block size is. So then we set our device buffer, and then we're going to send one of these specific commands. We're saying by default it's going to be a read block, but if write is set and there's more than one transfer block, we'll do write multiple. Otherwise, if write is set, we'll say write block. Otherwise, if it's not write and there's multiple blocks, we'll do read multiple. So then we'd kind of do a loop here. We're going to retry 3 times. Essentially, this usually always succeeds on the first time, but if for some reason the device is slow, maybe card issues, it might fail the first time and we have to retry. So we give it a 5-second timeout, way more than it needs, but so we're essentially sending this command, one of these types of commands, and just checking the status and retrying if necessary, and then we return true. So that kind of covers all those pieces. The next piece that I want to talk about again is that register process. So I created another header here called io.h, and so I'm creating an abstraction called an IO device. So let's see, we have an IO device is going to be some kind of device. It's going to have a name. It's going to have some kind of internal data, which we're just using a void pointer for. The data may or may not be set. And then optional functions that if it supports it, then it'll be set, otherwise it'll be null. So it can have a read function. The read function returns int, takes in the IO device, takes in a void pointer, which would typically be the buffer, and then a U32 for the size. And then a write function, a seek function that takes in a U64 value, and possibly an open and close. And in the Emmc device, we're setting that up to be an IO device, and it has a read and a seek for now. We'll implement the write later, but I don't think it's going to need an open or a close, because really all it's doing is reading and writing and seeking. So in addition to this, we have a function register device and find a device by name. So under drivers shared, I have this io.c where we essentially have a maximum number of devices. I just put 10 for now. We're just using an internal array of pointers for this. So if you want to register a device, you'll pass in the pointer to that device you want to register. It'll find one that's in the array that's null, and that means okay, there's an open section for one, and it'll set to that. And if we want to find one, we just kind of loop through the array and find one using this stir equals that's name is equal to the name passed in, and then we return the device. So in the Emmc init function, let's see, down here actually we have our IO device, which we're calling an Emmc IO device, and we're setting it equal to .name equals disk, .data equals the address of the actual Emmc device object, and then the .read is set to Emmc IO read, and seek is set to Emmc IO seek. So Emmc IO seek just calls, let me see, Emmc IO seek just calls Emmc seek, and Emmc IO read just calls Emmc read. So this is just kind of an abstraction so that we can actually interface with an IO device not knowing what the actual implementation is, and having to know, okay, I need to call Emmc read. I just want to say I have a disk and I want to read from that disk. So that's what this is for. And I actually set that up the same way in the MUArt, because if you think about MUArt, so that is a IO device as well. So in our MUArt device, I set the name to MUArt, and there's a read function and then a write function, and then I register the device. So then I kind of changed the way printf works, because if you remember the printf from like a really early video. Now that I gotta find where I put this thing now. I think it's under MISC. Yeah, printf. If you remember before, we would pass in a put C function, and we would just pass in MUART write. So now what we do when you initialize printf, so our init printf method takes in an IO device, and so we're initializing printf with an IO device, and then instead of looking for a put C function, we just call our printf device write printf device, the address of this character, and 1, because it's only 1 byte. So now in our kernel you'll see, let's see, right after our uart init, we do init printf, and we pass in IO device find with the name MUART. So now we have more of an abstraction. So I suppose eventually a printf could be like a video device or a eMMC device, maybe, that we want to printf to. So that's what the whole purpose of that is, just to create that abstraction layer. So what's new in this is we have our eMMC init. So this is called by the kernel after our after most of our initialization. If that fails, we just print it out and return. So then we're printing out eMMC disk is initialized. So what do we do once we have the disk initialized? I want to read the master boot record, and if you're not familiar with a master boot record, it's what's basically at the very beginning of an MBR type disk, which the Raspberry Pi ones are going to be. So the master boot record contains some boot code, which is this many bytes. It contains 4 partition entries and then a boot signature. So a partition entry, it's going to have a status value, the first sector as a CHS address object, which has the head and sector, cylinder high, cylinder low. This is all data that kind of used to be used in the old days when we had these spinning disks that had heads and sectors and cylinders. But what we actually really even don't use this. We use the first logical block address sector. That's the LBA sector. So this tells us the address on the disk where this partition starts. And it'll tell us the number of sectors. That'll give us an idea of how big it is. So these are the 2 real fields that we need, but these are all data that are read from that master boot record section. And then this boot signature has to be this value in order to be correct. So if it isn't this boot signature value AA55, then we know it's invalid. So, and again, we're using this packed. If you remember that from the previous video, if you're going straight to this video and skipping that previous video, this code here is not going to work, because you have to enable the MMU before you can use unaligned data, which is what this packed thing does here. So just watch the previous video if you're not familiar with that. And so what we're doing is creating our master boot record object. We're finding the eMMC device by looking it up by its name disk, and we're saying disk read, passing in the disk object and the address of our MBR structure and the size of the MBR structure. So that should return us 512 bytes. Then we check to make sure the boot signature is valid. If it's not valid, we'll print that out saying, hey, the boot signature is invalid. Then we just kind of loop through each of the partitions and print out its data. If it's type of 0, that means it's not a valid partition, so we just break after that. So, and the Raspberry Pi disk by default should have a 1 FAT32 partition and then an ext4 or ext2 partition. So then I'm just printing out some of this data for the partition, and then I'm sleeping 15 seconds just because this is the stuff we're interested in for this video, so I want to be able to see it. So I guess we can just go ahead and let me open up a new terminal and we'll run the build here. So let's say make clean make. Okay, so that There's our disk there. I'm going to take the disk out, put it in the Raspberry Pi, and let me boot it up, and I'll switch over to my screen here. Here we go. So it is booting up now. We initialize the MMU. You see we eMMC disk initialized, the read disk returned to 512, that means we returned our master boot record, and here's partition 0, which is type 12, that means it's a FAT32 partition. Oh, let me power it off before we lose our place. So partition 0 is type 12, number of sectors, its status, and where it starts, because this is the cluster that it starts at. And then partition 1, type 131, which is some kind of Linux format, either ext2 or 4, I think. And then the number of sectors, the status, and the cluster that it starts at. So that would actually be the logical address times the cluster size. So I think that kind of covers everything in this video. So hopefully you enjoyed this video. Again, I know it's a lot to kind of cover, but if we look at this file, just eMMC file alone, it's like 800 lines of code almost, and then this eMMC clock is another 100 lines of code. So I want to kind of do this format so that I wasn't trying to type it as I'm going and taking 10 times as long. So again, I hope you enjoyed this video and learned something from it. In the next video, I'll start covering the FAT file system format, so we'll actually at least read the FAT data and be able to list out directories. I probably won't get into reading and writing reading files, at least to start with, until a following video. But the first video I want to at least go over how the FAT is structured and how we can read data from it, and you know, read directories and stuff from the disk. So that we'll get into in the next video. I hope you enjoyed this video, and if you have questions, please comment on the video. Like the video if you like it. That's how I know what content to spend time creating, and of course subscribe if you want to see more of this content, and join our Discord channel if you have any like longer questions. I keep saying channel, Discord server, so I'll have the link to that in the description. So just join that if you have any further questions, and me or someone else I'm sure can help you. So, and thanks again for watching.